This lesson is going to be about wave speed, and the learning target is to be able to calculate wave properties and speed. A big idea in waves is that waves transfer energy but not matter, and so we want to keep that in the back of our minds as we're going through this is that the reason why waves are important to us is because they transfer energy. The energy that gets transferred from this water droplet down to the water, the potential energy that this thing holds, gets transferred outward through the waves. And the energy of the energy that the waves are carrying depends on the properties of the waves. So if we can understand the properties a lot better, we can understand the energy. And then from that, if we can understand the energy, we can understand the usefulness of the waves and how we can use these things. And so these calculations and the relationships that we're looking at in this lesson are going to help us to understand how the waves that we're looking at are useful to us, or what they can be used for. And so keep that in the back of your mind that waves transfer energy, but they do not transfer matter. Look at how waves are formed. When we're making waves, these waves are formed by a vibration or some sort of input of energy. One vibration equals one wave. This little guy is sitting down here, vibrating the end of this rope. Every time he shakes that rope, we get a new wave that's formed. And the way that he moves that rope, the way the source is acting and putting energy into this rope, is going to affect the properties of these waves, whether it's the amplitude, remember that is the height that the wave is above the rest position what the rope would normally be at otherwise. It could affect the wavelength, the distance between the same 2 points on a wave, from the crest to crest or from the trough to trough. Right? And it could also affect the frequency. Remember, if I have a certain point here, and I want to see how many waves travel past that point each second, that's my frequency. If I have a lot of them moving through, this wave is either moving very, very fast, or it's really, really bunched up like this. Not exactly like that, but something like that. Then I have a really high frequency. And so this source has a huge effect on these properties of the wave. And so if we understand those properties, we can understand the source and we can understand what we can use these for. So the wavelength and frequency, how are they related to each other? Well, if I have some sort of a barrier here, again, my point that I'm watching these waves move past, they're going to be moving in this direction. And let's say these two waves are moving at the same speed, right? So they're traveling the same distance per second. If I have a high frequency, where there's a lot of waves passing by this point every second, these waves have a very short wavelength, right? Because we got to bunch them up. If I have a low frequency where I do not have very many waves passing by this point every second, I have a very long wavelength. You can see how they're spread out from each other. And so wavelength and frequency are connected in something that we called an inverse relationship, meaning that as frequency goes up, wavelength, which we show like this, goes down, right? And as my wavelength goes up, my frequency goes down. So they have an inverse relationship to each other. So given that the wave speed is the same for two waves, frequency and wavelength have an inverse relationship to each other. But if we have these values, we can actually calculate our wave speed, our frequency, and our wavelength of a wave, given that we have two of the other values. So the way that we measure these is wave speed, we're going to be looking at meters per second for what we're doing here. This could obviously be anything different depending on what this wavelength unit is and what this unit of frequency is. This one here, hertz, is pretty standard here. So oftentimes the wavelength will change, whether it be nanometers, millimeters, centimeters, picometers, whatever that needs to be to account for the waves. But a lot of times this frequency is going to stay the same. And if you ever see something like this, s to the negative first, that's hertz. Because what this frequency is saying is number of waves per second. Right? And so when we note this seconds down in our denominator, we can show that as s to the negative first. So you might see this every once in a while. That's the same as hertz. But as long as our wavelength is in meters and our frequency is in hertz, our units for wave speed are going to be in meters per second. If my wavelength was in something like nanometers, then my wave speed would be in nanometers per second. They just need to match up. And so we can use this equation to calculate these different properties of our waves. So let's see how this works. We have a situation: a mosquito beating its wings produces sound waves with a frequency of 700 hertz and a wavelength of 0.5 meters. We want to know how fast the sound waves are traveling. So we start with our wave speed equation. Wave speed equals frequency times wavelength. And we can check our units here. We know that wavelength is in meters, and that's the same as in a problem. We've also got our frequency in hertz, and it's the same as in our equation. And so our wave speed should come out to something in meters per second. So we can set this up this way. I'm just going to use WS for wave speed equals frequency of 700 hertz multiplied by 0.5 meters, and my wave speed equals 350 meters per second. And I know that's my units because I have meters here, and this hertz really means 1 divided by seconds. And so when I multiply by meters, I end up with a unit of meters per second. So this would be the answer to this problem. So we can use this equation to calculate the other properties, not just wave speed of this. So we start out with the same equation, and I kind of simplified it here. Wave speed equals frequency times wavelength. And this is the Greek letter lambda. That's used to represent waves length. And so when you see that, we're really talking